This one.
Here, okay. Give me just
Hello, test, test, test. All right.
All right, so we're going to start in a couple of minutes, so hopefully we're going to have some more people trickling in. So remember to try to leave a little bit the chairs on the edges free, so when people join a little bit late, that there's space. Yeah. Bell? We had a bell? I didn't know we had a bell. Who held the bell?
No idea, but that was the thing that they always used to be a bell.
Okay. Okay, so
I mean,
maybe we should
find some random stuff.
Yes.
Just like ring the bell or something.
Do you have a bell on your phone? Yeah. 2 more minutes?
Do the MIT thing starting at 4:05.
Yeah, that's what I was thinking. Like, am I late? And it's like, oh, time started. Nice.
announce Keynote.
Should we move to the middle? All right, everybody. So please find your seats so we can get started. It is my great pleasure to introduce Tomás Lorenzo Perez for our first keynote speaker. He is a professor of teaching excellence at the Massachusetts Institute of Technology. He is his group is part of the famous computer science and AI lab there at MIT. He's won multiple awards, including the IEEE Automation and Robotics Award. I think a lot of people will agree that one of the things we really like about Tomás's papers is the fact that he sort of integrates task and motion planning and learning in a really nice way. So there's a lot of insights into thinking about how learning can fit into these larger frameworks. And today, he's going to be talking about how robots can understand the world and general robotics. So once we have your slides up, there we go. I'm going to hand over to you.
All right, thank you. I feel like I'm in a TED Talk, and this is weird, but anyway. All right, so I'm happy to be here in Munich. If I become incoherent at any point, it's because I'm depressed about the United States, but aside from that, I'll try to be somewhat coherent. Let's see, I guess I was invited to present a different viewpoint from the traditional one, and then I'll see if I can do that. Anyway, so let's start with goals. My goal is to build general-purpose intelligent robots. When Leslie and I used to present this slide, a few years back, everybody said, well, you guys are nuts. I mean, what are you doing? But now this has become fairly common. A lot of people are trying to build generalist robots. Companies are saying they're doing that too. But I'm going to probably have a slightly different viewpoint than most people. I've been around for a long time. I started graduate school in 1974 to work on robot manipulation. So it's been 50 years. So I have a slightly idiosyncratic view of the progress of robotics. So let's see, if you've kind of started in the field in recent years, you might think, oh, well, robotics, there's been this kind of growth in generality from the early days to the current days, and, isn't that awesome? But that's actually not the way history works. The history is actually a pendulum, not an arc. And this is not my idea. As you can read about it. And I went, once I read about it, I started, I went looking for slides to illustrate it, and I ran across this slide, which, says that the progress of history of culture and so on is three spots, three positions between asceticism, humanism, and hedonism. Of course, with current events, there's only two of them. One is sanity and insanity, and you go back and forth. But anyway, I won't say much more about that. And then, I decided to adapt this slide to robotics and to highlight like the three ways in which we try to build intelligent robots: imitation, policy, and planning. Now, since this is robotics, when you see a pendulum, it's an inverted pendulum. So I have the inverted pendulum theory of robotics for you to share. And I'd like to give you a little history of what's been happening in robotics from my point of view. This is, idiosyncratic, my point of view. Okay, so robotics started with imitation. The Unimate was the first industrial robot, and it was a tape recorder. It was literally a tape recorder. You let it through a motion, and it played it back. Oh, the sound doesn't work. The best part of this video is the sound, but it's not playing. This is the Unimate in 1967, and it was. I had to add that little thing to make it a modern video. It would play back stuff. It was very accurate. People used it in industry, and it was an important step. And of course, this is the best part of the movie. There you go. Very British. So the idea, of course, is that okay. So is this general? And we all know that recording a trajectory is not very general because it depends on the world being in a particular state for it to work. Let's leave that there and consider the other kind of leading brand. And this is actually not very well known. This is the MH1 robot, 1961. It was Heinrich Ernst's PhD thesis at MIT. Look at the advisor. I don't know if you can see it. It's Claude Shannon, Shannon Entropy, that guy. This robot had a set of sensors on the hand, which were contact sensors. And he developed a policy, a sensory motor policy, for stacking blocks, and it would kind of feel around on the table until it felt something that it thought was a brick, and picked it up and felt around for some place to put it, and it could feel around for bricks or boxes. So this was a sensory motor policy. The way if I changed the colors a little bit, I could submit it to CoRL. But that was 1961, right at the same time in which the Unimate was announced. Within a few years after that, the people in the AI community, such as it was back then, said, okay, well, all that stuff isn't good enough. It doesn't generalize well enough. So they built Shaky. This came out of SRI. And it's the first robot that you could call intelligent, I guess, in some sense. It was amazing. From this work came task planning, motion planning, A-star, vision, everything. Let me show. Okay, so it would build a plan based on a symbolic description of its environment. And look at it. This is why it's called Shaky. Every time it stops, it'll go. So it would look to see that the space was clear before going through a door. Oh, that was Charlie Rosen. Ask me about Charlie Rosen stories later if you want. Anyway, so Charlie put the gremlin, put a brick in the way there of the door, and Shaky would replan and execute again because it had seen the brick. So it was an awesome intelligent robot, really. So what happened historically is that it was forgotten, like truly forgotten for lots of years, and everybody switched to, okay, well, we don't want the mobile robots anyway. So everybody was doing hand coding of robot programs to implement particular policies. Back to policies again from planning. We'll see this as a pattern. The good thing is that during this time, the whole infrastructure for controlling robots and arms, especially, kinematics, dynamics, and control, was developed to support this kind of programming. So we've benefited from it enormously. But the problem, of course, is that these policies were narrow. You'd apply them in a particular situation, let's say an industrial task, but they didn't generalize very well. When I started in robotics back in 1974 or whatever, So I focused on it as a programming problem. Okay, so we've got these robot programs that, if you move anything out of place or if you put something in the way, just fail completely, won't generalize. So maybe we could do automatic programming. We could plan the motions based on given a sequence of high-level task steps like pick, place, grasp, move, and so on. Maybe we could plan those motions automatically. So I developed this idea of configuration space obstacles, and that you could plan around the configuration space obstacles. And this worked pretty well for low dimensions, but didn't scale to high dimensions. 15 years later, the smart people actually worked out a way that does scale to high dimensions. The motion planning algorithms that are sample-based that we know and love now. Now, the thing about this is, from my point of view, it was, hooray, we've solved the problem, right? So what happened? Everybody went off to behavior-based robotics. The rationale was one that we've come to become used to, which is, oh well, planning is too slow. So Rod Brooks, who was my first postdoc, said, okay, we can ignore planning. We can instead write a policy that is sufficient to solve the tasks that we want. And this was an amazing success. There are, I don't know how many million Roombas in the world, and they were based on this idea that you could implement a policy that was very robust and would do the task. So that pendulum swung all the way over again. I mean, not all the way over, but back to policy. So then, if you go back forward another decade, we get to probabilistic robotics. Wolfram's there. Most of it was focused on navigation and SLAM and things like that, which we live with. But one of the things that happened was also an interest in planning in the presence of uncertainty. And my colleague Leslie, who's hiding in the back writing code, is a pioneer in this area. And I got depressed, not just because of the election, but because of other things, and left robotics for 10 years. When I came back, I said to Leslie, hey, how about we combine this motion planning stuff with the POMDP stuff and make some great robots? And Leslie said, nah, that won't work. And anyway, but we did kind of work on it, and our student Kai-Jen Shao did some excellent work on doing planning for POMDPs. And the great thing about POMDPs is that they allow you to look at sensing and acting in the same framework to try to produce motions that gather information and so on. So we were really happy with that. So what happened next? Any guesses? RL, right? So the AlphaGo came in, and people got all excited about RL again. The new component being that with learning, maybe we could learn the policies that we had so much trouble writing before, right? So we'd been trying to write policies by hand for a long time, so maybe we could learn them. And the results are today amazing, right? You see all these robots walking around with RL, but you still don't see long-range manipulation with RL. At least I haven't seen it. I'm sure somebody outside will tell me that I missed it. But anyway, I'll postulate that. And then, what's happened since is that, in the last few years, there's been a kind of focus on using imitation learning to try to learn policies. And that's been enormously successful right now. But we haven't seen long-range manipulation out of that either yet. And it's an open question whether we will, but let's imagine that we can. Here's my message. Instead of flipping back and forth between all these things, maybe we should try to think about putting them together. So my new my new slogan, and I propose we adapt this as the slogan for CoRL, is, everything is everything. Everything is all you need. So that's kind of like the main moral of my story. And the rest, what I will try to do is try to make it plausible that this is a good idea. OK, so having said that, let's talk once again about goals. And I'd like to make a somewhat distinction between two types of goals, two kinds of tasks that we face in robotics. One are kind of motion-oriented tasks, and that involves control, the real-time stuff. These kinds of tasks are the ones that are very hard to teach someone. Walking is an example. If evolution hadn't kind of tuned you for that, you'd have a hard time walking. Juggling, riding bicycles, playing tennis, lots of stuff that needs a lot of practice to get good at. And I'm going to include motion planning in that. Okay, it's a kind of motion task. Then there's tasks, the stuff that is superficially very complicated, but actually, in terms of motor skills, very simple. It's the kind of thing that's very easy to teach a person to do, because they already have the motor skills, and it's a question of how to deploy them. So roughly, we want to bring those two together and address them because they do influence each other. Sometimes people, when we talk about task and motion, think that it's task then motion, and that's not what we mean at all. We mean task and motion integrated together, and that's what I'll be trying to talk about. Okay, so you can think of this as physical decision making, and there are a number of key questions that come up if you're going to build a system. I mean, even the simplest kind of system. There's kind of what representation you have, what kind of actions you have, and what kind of mechanism you put between them to go from your representation of the world to the actions. And there's a whole bunch of challenges, right? You have physical and geometric properties. You have high degree of freedom robots. You have to make long horizon plans, and you have to do all these things in a time-varying environment. So the question is, how do we approach this? How do we do this? Does anybody get the reference two paths diverged? Anybody read poetry anymore? Not in this crowd. It's Robert Frost. Anyway, so we have two paths. These are caricatures, but nevertheless. So one path we can think about is we're going to get a big, massive system. We're going to put a lot of data into it, and it's going to solve the problem. Okay, that's one road. And you might think that this, when I say this road, maybe it's, it'll be slow at the beginning to gather all the data, but then it'll take off. And then we have the other road, the less traveled by, in which we try to take all possible advantage of anything we can get our hands on to get some leverage on the problem. So what we know about the structure of the physical world, what we've learned from algorithms for many years, that their abstraction, modularity, composition, and inference matter, and our accumulated cultural knowledge, represented these days by LLMs. There's no culture beyond that anymore. Anyway, so so maybe this path would lead to faster startup, and then maybe, plateau, and we'd wonder where the crossover is. Or maybe you believe that it's actually the other way around. I don't care. The only point is that there are two paths, and they're both interesting. They're not trivially one dominates the other. At least that's my position here. So given that that's the position, I'm going to try to focus on what I consider to be three key ingredients for generality. These will happen to align with what I said the lessons we've learned in the past are. And I'll try to illuminate, or at least exemplify some of these points by doing work that's stuff that we do in Leslie's and mine lab, or at least our students do. Okay, so modularity is one. The second one is planning, not surprising. And the last one is compositional abstraction. So I think these are the three key ingredients to get generality, and I'll try to work through them. So let's start with modularity. One thing about modularity is that it has a number of potential advantages. It allows you to maybe generalize more with fewer samples because you can focus on one module at a time, so you factor the problem and you factor the data requirements. And it also, in some cases, allows you to do things incrementally. Now, whenever you have a modular system, you have to worry about representations. What goes, what's on the wires. And this used to be a very troubling question. So we used to worry about this a lot. And then LLMs came along, and the answer turns out to be text, which is weird. But anyway, so, text, images, and I'll make a plug for putting 3D in there as well. So in fact, let's talk about, this is a possible modular policy representation. And let's talk about scene understanding, because why would we want to do that, right? So the point is that you don't want to have every one of your actions have to learn vision and control and all these other things. So maybe you could separate them, right? And learn a representation that was useful, just like text is useful in many settings, and images are useful in many settings. Maybe 3D would be useful in many settings. A couple of our students, Aditya Agarwal and Bipasha Sen, who's actually Pulkit's student, have been working on a system to try to get 3D reconstructions from a single view. And the nice thing about this is that there's a lot of pieces around that actually solve pieces of the problem. And if you can put them together, you can do pretty surprisingly good reconstructions. Now, of course, let's see, maybe Jitendra's here, and I can blame all the errors on the computer vision people. Anyway, many of the proposals for high-level reasoning and planning always start out with assume an object-centric representation. And every reviewer says, well, where are you going to get that? So our answer is computer vision. It is now feasible, to actually do 3D reconstruction. And the definition of what an object is a bit slippery, but it's okay. It's good enough, especially if you can get out something which is a generative model that can give you multiple answers. You can actually think about having an object-centric representation without being embarrassed. I propose that from now on, we're not embarrassed about saying that. Okay, so modularity, in the sense that it buys us this kind of decomposition and, maybe factors our data requirements and gives us some advantages, is a key property. Now, let's talk about planning. There's a great talk from Noam Brown. He gave it at Berkeley recently and a couple other places. If you haven't seen it, please go see it. It's awesome. He's not paying me or anything for this. He has this wonderful example of the impact of search on poker. He said, it turned out that having just 20 seconds thinking for 20 seconds was better than boosting the performance and scaling the model by 100,000x. I love that. Okay, so this, it sounds outrageous, and you could say it's about poker, but I think it's about everything. And that kind of idea is like central to getting systems that generalize. So, why would you want to do search and planning? There are a couple of reasons. One is that you're focusing on searching the problem that you have now, not all possible problems, right? So if you need to get a policy that covers everything, you have to think about everything. And whereas the planner only has to think about the problem that you have now. Our student, Jiazhuan Mao, has shown that policy learning, if you analyze it from a circuit complexity point of view, in many cases has these exponential behavior. And it's kind of not surprising. If you need to cover a wide range of possibilities, your policy is going to be horribly complicated, which is why we had trouble writing them, and we've had trouble learning them whenever things get too long. So, planners are trying to solve just one problem at a time, and that can help. There's another reason why it's related, why planning helps. This is a wonderful quote from Popper, letting our theories die in our stead. And the idea is that if you've got to learn policy, you have to get it right? You want to execute the policy, whoop, whereas a planner, if you can evaluate if you know how to evaluate your suggested actions, can actually think for 20 seconds and avoid having to jump off a cliff. Now that's not only a kind of safety issue; it also reduces how difficult the policy has to be. It can be a little off and still be useful when combined with planning. So this idea of runtime inference is becoming more and more prevalent. So you're all familiar with chain of thought and tree of thought, and I'm going to do a Turing machine of thought next. But a lot of people are pursuing this idea that you can, with some runtime inference, improve predictions substantially. And there's this alpha geometry system recently that basically uses a theorem prover on the side as a way of doing additional inference to get much better performance on mathematical problems. So this is kind of creeping in, and we should adopt it in a big way. I'd like to show one example. This is from Yulun Du, who's one of our students who just graduated. And many Google collaborators. It's a paper from Google, so it's got 50 people. I'm sorry, the Google people, you're doing wonderful work. Keep it up. But it's hard to reference the papers. This idea of video language planning is basically to take 4 modules, which are implemented with foundation models, and combine them with search. Let me try to talk through it quickly. The idea is that we combine an abstract policy, something which gives us text actions given an image and a goal. Then there's abstract heuristic. Now, you probably learned about search heuristics when you were in college, right? And you've forgotten by now, but anyway, it's something which tells you a number of how many steps to reach the goal. And there's a transition model, which given image, text, and action gives you an image sequence. And then there's a control policy, which could be just a set of policies you've learned ahead of time, or inverse dynamics model, which takes images and produces actions. So you take these 4 pieces and you query the abstract policy, not for one action, but for k actions. And then you do compute the next states using your transition model, the way you would in any graph search problem. And you do beam search to get an abstract action sequence, and you use your heuristic to rank what you're going to do. So this is, putting fruits into a drawer. And, I love the fact that, it actually can generate the misses as well as the successes. But anyway, by doing a little forward search, you can actually then select the actions, because the generative model is actually giving you, some ability to choose which actions you pick, the k best ones, and then your heuristic, which you've learned, allows you to pick, to choose one path over the other. And at the end, you can construct a sequence that you can then execute by kind of looking at it. So this is an example of both kind of modularity at play and also the idea of using planning to strengthen the effectiveness of the policies. Okay, so I've said I've kind of briefly illustrated two of the points. The last one is maybe the most important one. It's kind of essential to the planning component, really, and it's the idea of compositional abstraction. The idea here is that we have states and we have actions, and we want to think about abstractions of them because they allow us to generalize in ways that we couldn't if we had full state descriptions and low-level actions. So for example, holding an object is an abstraction of a state, and it's a classifier which, when applied to the input, tells you whether it's true or not, and you have in and so on. And these can be used to describe the preconditions and effects of actions. Once again, once upon a time, 3 years ago, when we said this, people, this kind of stuff, people would say, but where are these symbols going to come from? And now, of course, we have the universal answer from LLMs, of course. We'll see more about that later. But the idea of having symbols and them being useful is becoming more acceptable, which I'm very glad about. Anyway, there's also actions, right? And the actions represent are a temporal abstraction of a policy that you can execute. You can grasp an object, you can put it in someplace, place it, or whatever. And the point about these abstractions is that they actually make planning much more efficient because you don't have to think about the 1,000 hertz pattern of torques required to do them. So these are very important as a way of achieving compositional generalization. However, I was being facetious about the LLM thing. Could you tell? No, it's actually halfway. So the thing is, the abstractions that you want need to have certain properties to get them to fit together nicely and actually be able to represent what we want. And that's the one way of visualizing the way manipulation and interaction with the world works is that there are these submanifolds in the configuration space that are defined by constraints. So for example, we can have a manifold in the space which is moving to a grasp, and that is constrained only by the presence of obstacles, say. And we can have another one which is moving while holding something, and that is different because now the object moves as well as the robot moves. So these are two different modes. And the key thing is that these modes, for example, intersect. And the intersection is due to the fact that they both have holding. One as an effect, and the other as a precondition. So you can chain them. You can decide how to chain them based on the description of the actions, these operators, in terms of these conditions on the state. So then, after that, you have to ground them. So given a particular action, okay, move to grasp, you have to move to a place that's at the intersection of the manifolds, which is something that you characterize in the by the definition of the action, and then move while holding. That also has a set of constraints and has you follow a particular path. So the idea is that these bunch of symbols together actually describe something which is physically constrained and allows us to solve complicated problems. So for example, if you want to put all the food items in the fridge in some situation, you can have a task plan, which is at the high level the sequence of operators that you want to apply with maybe the objects chosen. We call that a skeleton. And then for each one, you can then try to find the grasps, trajectories, poses, and so on that are, and check whether they are physically plausible. And if they aren't, you can backtrack. There are more efficient algorithms, but that idea at least works for now. So in this task and motion planning framework, there are a number of things you need. You need a task domain specification, which is roughly, imagine that I was interested in making soup. Then it would be a set of operators that would tell me what the steps I need to do. We'll talk more about that in a second. Then there are these predicates, things, the state abstractions, things like in and holding and so on. There's the parameter samplers, the way that you fill in the variables that are left in these operators, so the paths, grasps, and stuff like that. And then the transition model, which is what effect the different actions have, also described in terms of abstraction. And these can be combined with existing planning algorithms so that if you get a state description and a goal, then you can produce a sequence of actions to do that. So that's basically the deal. Now, we've worked on these kinds of things for a while, and one project that Aidan Curtis, Xiaolin Fang, and Kalen Garrett. Kalen used to be with us, and now he's at NVIDIA. So he keeps popping up because he hires our students as interns. And so it works for both of us. It's good. Let's keep doing that. Kalen's here probably somewhere. Anyway, the idea here was let's do task and motion planning, but without any models, okay? So this is not like, CAD system models or anything like that. You get perception, you get a point cloud, you fill it into a 3D object by doing, in this case, a simple segmentation and kind of shape completion operator. We look forward to actually using the more sophisticated ones that we talked about earlier. Then you run into the task and motion planner, you execute it, and if it succeeds, you keep going. If it doesn't succeed, you try again. So it's a very simple approach to dealing with actually partially observable scenes in which there's a lot of occlusion. So let me give you, this is kind of our favorite example. So the setup is, you'll see Kalen show up, dump some stuff on the table, and notice that only one object is visible. Okay, so only the Cheez-It box is visible. So the robot has been told to put everything on the table, so it does, and puts it in the middle of the region. Makes sense. But now, oops, there are a couple more objects. So it says, okay, they're not going to fit in here. So it takes the box out, puts these other objects, and it has to take the box out because you see that you wouldn't be able to reach the back if the box was in the way, and then puts it back. So this is I think a quite sophisticated operation, which requires a lot of understanding about the arrangement of the worlds, which we got by this search process, roughly. And you can, it generalizes over objects, it generalizes over goals. This is a very different, weird goal that I don't know where they came up with this one, but anyway, put each object in the bowl of the closest color, and it sometimes misses, but it keeps trying until it does it. So this is a good one too. Is what's an object? Okay, so it's put all the objects on the blue mat, but these objects keep proliferating, right? And it just it keeps trying. Okay, well, that was good. Keep going. So I mean, it's a remarkably sophisticated, greedy policy that is built upon a kind of high-level operations. The ability to detect what objects are in the scene, choose a grass, choose paths, and so on. And this is, now not with the PR2, but with the Panda. And what we use this for is we do cross-embodiment generalization. It's the same system running on a different robot. So it also shows that there's a wide variety of goals that you can achieve. Now, a lot of what we do is pick and place, but I claim a lot of the world is pick and place. But anyway, let's not argue about that. There's also, this is work by Rachel Holliday, and it's basically model-based in this case, it could be extended, but it's using different estimates of the frictional properties to open a child-proof model. And has 4 different ways, depending on which, what you estimate about the friction of the different, the different objects, and it actually has to push down and it evaluates, which one is likely to work and so on. So this is an extension beyond the classic sort of pick and place case. And also, going back to POMDPs, so you can also define planning in the belief space. So the classic solution for planning in partially observable domains is to think about planning in a MDP on the belief space, on the set of states that you could possibly be in at the moment. And this is a task that's very hard to specify as a sensory motor policy because it involves kind of searching around and exploring different alternatives in order to do the task. And this is done completely by planning. It's not, it wasn't taught any of the pieces. It has kinematic models of the drawers and so on, but it decides that it has to close one before opening the other and so on. So again, it shows the power of the kind of planning idea in another domain. And there are a lot of papers that I've read that are, an LLM or a VLM can do planning. We don't need task and motion planning. And I'd like to propose a different idea. This is Shujian Yang and Kalin again from they did an NVIDIA, and the idea is, well, let's try to get the VLM to tell us something. And if we're going to ask it to make chicken soup, that's actually a cultural piece of knowledge, and we shouldn't really have to kind of build it in. We can look it up. So let's get the VLM to tell us a sequence of actions to make chicken soup, because our TAMP planner isn't going to figure that out. However, the VLM is going to tell us to do a bunch of dumb things that are dumb only because it doesn't know the embodiment and it doesn't know the details of the geometry. So if you run it, the VLM tells you to do this, that, and the other thing. And some of those are good, and the TAMP planner says, OK, I can do that. And some require a lot of re-specification. OK, well, I can't just do that directly. I need to move this and move that and so on to get it out of the way. We can do that by putting the two systems together. And one of the things that's actually the hardest is actually incorporating the embodiment. So, this is this Rummy, which is this robot they have at NVIDIA, which has enormously long arms. And when asked to put that object inside the pan, it can just reach it and reach over the pan. But if you take a PR2 with 2 arms, it has to pick up the object, close the door, and then put it in. And if you have a PR2 with 1 arm, it has to pick up the object, put it down, close the door, pick it up, put it in the pan. So these kinds of somewhat subtle embodiment differences are hard to capture, expecting the VLM to get those right. OK, here we go. All right, so I've gone through the kind of setup of building a system. So what I'm saying is start with a built-in learning and inference system, build in pre-train general compositional world models, do runtime inference, and we want to continually and compositionally improve and augment these models at runtime. That is, we want to be able to learn new things. And now, let's talk about that. So we've talked about these things that go into making a TAMP planner. So where do we get those things? So we had a line of work by Tom Silver, Rohan, Nishant, and Willie. Nishant is here someplace, so you can look him up, that tried to learn all the pieces of a planning system using inductive logic programming, to learn neural parameter samplers and neural parameterized policies using relational deep learning. So it's great work, which I encourage you to read. I am now, because of the world we're in, going to talk about a slightly different approach. So we can get LLMs to actually do operators for us, for example. So this is some work by Leo Wang, Jazwan, and Pratush Sharma So the idea is you give a natural language instruction and a set of available objects to the LLM, and you ask it to provide a symbolic plan, and given some prompts which kind of illustrate what that does, it can give you a plan. But typically, it sticks new actions in there that you don't know how to do. So, if it does that, then you can ask the LLM to give you a operator sketch. And it knows PDDL, and it knows the syntax, it's seen a bunch of it on the web, and it actually gives you a reasonable PDDL sketch. Now, the trouble is that the sketch isn't going to, you're not going to move a robot with that. So how do you actually go from a sketch to an actual, robot specification? So we did some work, Zi Wang and Kalin, on trying to take operator sketches with parameters, which is the kind of thing that we get there, and these are continuous parameters, and try to learn a constraint in the space of the parameters that says that it's a successful execution. And the way we approach this is by looking at a bunch of demonstrations or experiments, and to try to use, and we use Gaussian process regression to try to get a description of the whole constraint in the space of the parameters. This constraint could be used not just to execute the operator, but also to guide the acquisition of data by looking at the uncertainties that one gets from the Gaussian regression. So that was a nice way of putting, actually grounding an operator description. And the nice thing is that it gives you a complete characterization of the skill by characterizing the conditions under which that skill can be applied and produce the desired result. Because if I just have one skill, somebody says, okay, here's a program you can run, and it'll tie your shoelaces. Well, there are a bunch of assumptions that it makes about the world, and if we can actually specify them, we can then get other skills to make them applicable. Okay, I'm running out of time, but this is worth looking at. Okay, so here's a demonstration. Okay, so what did you learn from that? Okay, it's a trick, right? It's we call them a mechanism or a reusable policy. But the idea is that you've learned a strategy from that one demonstration. And the thing that's interesting is can we do that in other situations? And the idea is that you can think of this idea of modes, and a lot of modes change with contact, when you change your contact. So what you can get from a single demonstration is actually a sequence of contacts that are being made and broken. And that actually captures a lot of what's going on. So in this case, there's, you grasp the tool, you move with the, you hook the object with the tool, and then you place the tool down, and then you grasp the object. So that is an outline of a higher level operator, which can actually, because you know what the pieces are, you can compose them and get a more complex operator that you can use to shorten the horizon of your tasks. I'm going quickly to leave a little time at the end. And then, this generalizes over objects and so on, because it's looking for particular kinds of contacts, not description with respect to a full object or anything like that. Okay, there are other. Then I'd like to end with some work by Nishant, Tom, Willie, and Linfeng Xiao, which is actually focused on the parameters of a task. So if you have a sequence of parameterized skills that, in this case are on the spot robot, move, grasp, and so on, and a task distribution, and the robot starts out with a way of sampling values, which is not very good. But it has free time on its hand, and it decides to practice. And the question is, what should it practice next? And the idea is that you want to practice things that can actually improve your final behavior. And they have some way of characterizing your uncertainty about the parameters and then choosing a skill to practice. But I want to show you a video because it actually brings together many of the ideas that I've been telling you about. OK, so this is a room. There's a chair which is blocking access to the objects. And the spot is asked to put the objects inside the bin. And it has a set of operators that it knows what to do. And one of the operators is to sweep, to actually use that broom that's down there and actually sweep things around. At first, it has to get to the object, so it knew it had to clear the table, the chair out of the way. Now it's going to try to sweep. Whoops! It kind of, missed on that. It's too fast, so it needs to practice. So, given some free time, it chooses things to practice, and in this case, it has chosen to practice the sweeping operation. So it tries again with a different value, and there's no resets. It has to put the thing back so that it can try again, and then this time it works, but it still has uncertainty as to whether it has the right values. So it keeps doing this. I'm told that it's just running, and occasionally they have to change the battery. I understand that the next project is to get another robot to change the battery for this robot. Actually, if you have a spot, changing the battery is not that easy. So anyway. So, after practicing a lot, then it, kind of got better at doing this task. So it can, successfully carry it out. I want to get to one part here that's important. OK, so now the gremlin. So, this is, an homage to Charlie Rosen in the shaky video. And, here we go. That's Nishant. OK, so if you see him now, you can call him the gremlin. Anyway, but notice that what the gremlin did is put one of the objects up there on top where the robot can't reach. But all of you who have seen Monkey and Bananas can predict what's going to happen next. Who has seen Monkey and Bananas? It's forgotten. Oh, my God. Anyway, so, it picks up the object and puts it away. So, ta-da, OK. To summarize, you start with built-in fundamental learning and inference algorithms. You train general models. You do runtime inference. And you can learn to combine them as you go. And, there's lots of research questions. I don't have time to go into that. Thanks to all the students who actually did all the work, and Leslie and Josh and my colleagues and the funders. And that's it. Thank you.
All right, thank you, Tomas. So we have time for a couple of questions from the audience. All right, we already have one up here.
Oh, no, not Wolfram. No. He asks hard questions.
This was super exciting. Thanks. I have a question on your thoughts about this problem. I mean, the assumption is that you can somehow discretize your world and have like actions that are actually separable, right? So, but in many cases, like the optimal behavior mixes them up. Like the skill is not, I walk to the door, stop, and then reach out for the handle. I do this while I'm walking, right? Do we have an idea? I mean, particularly when you play sports, right? Then everything is this interwoven, right? So
yeah, no, we haven't thought about time parallelism, and that's that important area. Actually, even without the time overlap, there's interesting questions, which is I thought where you going to go. So we do assume that the skills are parameterized. So walking to the door and opening and so on, that's OK. It's not a fixed program you execute. It's parametric. However, I mean, there are some, actually there was an example in one of the previous orals, which was walking and then opening something with your foot. that's not something that we could expect to get out of the skills that we have right now. We would have to have some skill that was a combination of those that we could use, find the parameters for. So I think that's an interesting direction of going forward. We've thought about a variety of schemes, but it's a good point.
Thank you for the very insightful keynote. This was great. I think the question that I have in my mind is there are two paradigms that I can think in terms of data. One is we go and collect data, build, hundreds or tens of robot cells and do a lot of tasks and collect data. And the second alternative paradigm is data is already out there. Like people has been doing stuff and we have videos of them doing stuff. And let's go and just learn how to use that. Which one do you think is going to be the key to make robotics work?
Neither one. I'm sorry. No, actually, I mean, I tend to jump to the funny answers right away, but there's a grain of thought in there. Okay, so the thing that makes gathering data from a fleet kind of argument is really the diversity, right? So you need to be able to do a lot of things well before you can actually collect data to put them together. So just having many instances of the same thing doing the same thing isn't going to give you generality. It might give you very good performance on the narrow task. So there's a chicken and egg problem with the fleet idea. The watching people do it and trying to learn from them offers a different problem, which is the embodiment problem. And maybe we can get past that. But for example, people often talk about, use the videos on the web and stuff like that. But that doesn't actually capture a lot of the physical interaction. Maybe one could exploit it as a way of initializing a simulation which you could then learn from, or initializing RL or something. But I don't think that by itself it will actually be enough. This is, I promise, an idiosyncratic view. So this is my idiosyncratic view on that.
Should I go? Yeah? Okay. Yeah. Thank you very much. Very interesting talk. So I have two questions. First one is, are the modularity and compositionality related to each other? I think
yes.
they are. But
yes.
Can I ask the second also? And then, sorry. So I think it was great that you talked about robot learning, which means robot learning in the real world, not sim to real. That's not robot learning. It's policy optimization to me. So when you do learning in the real world, it means that safety becomes very important, right? So what do you think about that?
We will take whatever people do to use that there. No, actually, safety is a big issue. I don't think we have any particular insight into that. Maybe just a little one. A little one is the following. I don't think that we should ever be learning complicated things from scratch. So that we'll always should be learning incrementally on top of something else. So I think under those conditions, it's easier to characterize the safety conditions than they are in a, whoa, we're going to try to do everything. So I think that that's one thing. The modularity, compositionality thing, yes, they're related. But modularity is really at a very coarse scale, whereas compositionality, at least the way I talked about it, is a fine scale of representation. So, combining the predicates in an action and so on is compositional. It doesn't feel like particularly modular. It is kind of, but and the modularity at the level of there's a state estimation and a memory and so on. That doesn't compose in the same way, the same general way.
Here, I wanted to pick your. First of all, thank you very much for the great talk. I wanted to pick your mind regarding the prompt engineering that comes into the play when we are interfacing LLMs, VLMs, let's say, with just task and motion planners. You have to write 15, 30 examples of PDDL examples, and when the difference would be the context. So I think that as engineers, we could have done similar things with templating already. So where do you think this leads us towards the general purpose, task and motion planning for robots?
Yeah, this is a great question. Up until very recently, there were a lot of people who wrote papers that said, Task and motion planning may be okay, but oh my God, writing those operators is really hard. Let's replace them with an LLM where we have to write prompts. Right, so you say, whoa, which is better here? Okay, there's one thing that I want to stress, which is you don't actually have to write that many operators. That's really not where the bottleneck is. That's the whole insight in this mode kind of view, is that there really aren't that many physical modes. Where you end up writing a lot of operators is if you want to model a complicated task that has a lot of steps and so on, you end up writing a lot of ad hoc operators. But that's what you get rid of with VLMs, and they don't have to come in PDDL. They're really kind of stylized and easy to get from an LLM. You don't have to do complicated prompting for those. The hard one, which is in between, is predicates. So discovering the predicates, the set of descriptors that are necessary in order to describe the world, is hard, doesn't involve PDDL in particular, and VLMs can help. So I think that's my take on that.
All right, so in the interest of time, we're going to end there. Thank you again for Tommaso.
Mics again, please.
I want to remind everyone that we have the Keynote panel on Friday, so that shall be a good time for some additional questions for everyone. And now we're going to switch over to oral session 3, I believe.
And the oral session 3, which we are going to start now, is going to be chaired by Scott and Oir. And I'll let them start the session.
He is.
Can you
You're going to go plug.
And the next speaker, can you?
Okay, so we got the queue going.
I mean, I think Oir and Scott.
All right, we good to go? Awesome. All right, welcome everyone to the final oral session of the day. We have 6 talks for you in this session. The first talk will be differentiable robot rendering, and the speaker is Roshi Liu. And please take it away.
All right, hi everyone. My name is Roshi. I'm a PhD student at Columbia University. And today I'm presenting our recent work, differentiable robot rendering. This work is a collab with Alper Kimberg and advised by Sharon Son and Carl Vondrick. So we introduce differentiable robot rendering, or differentiable rendering of robot, or as we call it, Dr. Robot. Given the pose vector of a robot, Dr. Robot generates a 3D Gaussian spreading of the robot body under that pose. And it can then render an image in a differentiable way given a camera viewpoint. The gradients on the pixels of the rendered image can be backpropagated into the pose vector. Now, why do we need this tool? One of the most challenging problems in robot learning is for robots to have open world generalization ability is the lack of internet scale robot data. On one hand, we have real world robot data, which is rather limited and not very diverse, but is very useful for robot learning. On the other hand, we have internet visual data, including images and videos. They're highly diverse and abundant in quantity, but there's a big embodiment gap for them to be very useful for robot learning. With companies spending billions of dollars training impressive vision foundation models on these internet visual data, how do we leverage these internet visual data and these vision foundation models for robot learning is the research questions we want to answer in this project. We believe we need an interface to bridge the gap between visual data and robot control. which is what Dr. Robot is for. At a high level, Dr. Robot allows visual appearance of a robot to be differentiable with respect to its control parameters. Given a pose of a robot, Dr. Robot can differentiably render the appearance of the robot, and the rendered image can be passed into vision foundation models for various tasks, including text-to-robot pose optimization with clip or robot control with generative video models. These control signals produced by the vision foundation models are formulated as losses that can be back-propagated all the way back into the control space of the robot for iterative optimization. Before going into the applications of Dr. Robot, I want to talk briefly about how we achieve the differentiability of the rendering function. So we decompose Dr. Robot into 3 major components. Given the pose vector of a robot, we apply 4 kinematics to calculate the skeleton structure of the robot. We then apply an implicit linear blend skinning function to project canonical 3D Gaussians to the robot surface under that pose. We then apply an appearance deformation function to adjust the appearance of the 3D Gaussian spreadings to improve visual fidelity. And because the linear blend skinning function and the appearance deformation functions are implemented as feed-forward neural network, the whole pipeline is fully differentiable. And the parameters of these networks can be learned by minimizing the L2 difference between the rendered image and the ground truth image. Once trained, our model can render extremely efficiently at 100 Hz on a commercial GPU. Our model could be built from a URDF file of any robot with various form factors and any degrees of freedoms in just 15 minutes. Here we show the renderings of 10 of our robot models as compared with their ground truth rendering. In the pairwise comparison, you can see that our model is able to capture the accurate geometric and textural appearance of the robot as compared with the ground truth. Now let's talk about a few applications of Dr. Robot. In the first task, we apply Dr. Robot to perform robot pose reconstruction. Here we jointly optimize the robot pose as well as the camera parameters to minimize the L2 difference between the rendered image and the ground truth observation of the robot. After an iterative optimization process, we obtain the reconstruction of the robot pose trajectory as well as the camera viewpoint that is highly accurate compared to the original video. And this beats all the previous state-of-the-art methods in this task. And we could also apply this to different camera models, the videos captured by different cameras, including various extrinsic and intrinsic matrices, including Azure Kinect, Xbox 360, and Intel Resense. And our model could also be applied on in the wild video. Here we take a random UR5 video that we found on YouTube with an unknown moving camera trajectory. With Dr. Robot, we could perform reconstruction of the camera trajectory as well as the robot pose trajectory. And this robot pose trajectory can be replayed in a real UR5 robot in our lab. We could also apply Dr. Robot together with a text-to-video diffusion model. Here we take the stable video diffusion model and fine-tune it on the ASU tabletop dataset to achieve language-conditioned robot video generation. Once a video plan of a robot execution is generated, we can use Dr. Robot to extract the robot pose trajectory and to execute that in the real world. Here show some examples. We have a current observation of a scene. Our fine-tuned text-to-video diffusion model can be prompted by prompts like pick up the blue can or pick up the red block. And the video model can generate video plans of the robot performing the task described by the prompt. And we can basically apply Dr. Robot for inverse dynamics to extract the robot pose from the predicted videos. And the great Tomas was talking about Elon's great work, video language planning, where they train inverse dynamics models. You could apply Dr. Robot here for a better solution for inverse dynamics. We could also interface Dr. Robot with a clip model by optimizing the clip similarity between a rendered image and a text prompt. Here is an example where we're optimizing the pose of a shadow hand towards the prompt victory sign. And here are some more results from various prompts, including the rock on hand, thumbs up, index finger pointing, and the call me sign. Lastly, Dr. Robot could be used for motion retargeting when it's combined with a low-level vision model like a point tracker. In this task, we're optimizing for the action sequence of the robot such that the point tracks extracted from the rendered video resembles the motion in the target demonstration video. Here's an example where we optimize the hand motion of my hand, curling my finger, towards trying to transfer the motion to a shadow hand by optimizing the chamfer distance between the point tracks extracted from both videos. And here's another example where the hand-waving motion of my hand is transferred into a robot hand. And it also works on full-body humanoid robot. For example, here, the motion of my body is successfully transferred to a Unitree G1 robot. Lastly, we believe differentiable robot rendering, or Dr. Robot, is a crucial tool to bridge the gap between internet visual data and robot learning. And for more details, please check out our website and paper. And I'm happy to take any questions, and thank you very much for listening.
All right, questions? Got one in the back.
Hello? Okay. I think you show a demo where the camera was shaking with unknown extrinsics. Could you elaborate a bit more on how you handle the unknown extrinsics? Because I think it's a pretty common case in the wild videos. Thank you.
Yeah, so our differentiable rendering function is conditioned on both the robot pose as well as the extrinsic parameters of the camera, as well as the intrinsic parameters. So it uses a Gaussian spreading, so the rendered image is differentiable with respect to both the robot pose and the camera parameters. So when you're trying to reconstruct a video with an unknown camera, moving camera, you can just perform joint optimization of the robot pose as well as the camera parameters. Then you can basically reconstruct both the camera motion as well as the robot action.
Okay, thank you.
Mm-hmm.
Other questions? All right, I'll ask a quick one. We have another minute. So have you thought about how to maybe extend this to more complex robot scene interactions for maybe this robot interacting with an articulated object?
So the question is about extension to more complex scenes. So this work particularly only handles the visual part of it's a differentiable rendering function. So I think to generalize this to like contact, we probably need differentiable contact or like differentiable physics simulation as well. But I think it in terms of I think it could be a good complementary tool to a policy, for example, to try to inject some priors from some vision foundation models to the robot during the policy inference. So I think this alone might not be able to handle contact or differentiable simulation, but it could work with a foundation model or a policy model. Yeah. Thank you for the question.
Thank you.
All right. Thank you very much.
Okay. Next up, we have Dhruva Tirumala presenting Learning Robot Soccer from Egocentric Vision with Deep Reinforcement Learning.
Hi, thank you. So yes, I'm Dhruva Tirumala, and I'm here to present this work on learning robot soccer from Egocentric Vision with RL, that was done with these amazing co-authors. So why soccer? We're interested in the task of soccer from vision because it presents a number of important challenges that we care about as roboticists. It requires active perceptions, so successful agents need to search for the ball, track the opponent as well as the goal. It requires agile, dexterous, full-body control, while at the same time needing long horizon planning because the environment is dynamic, partially observable, and involves multiple agents. Now, this problem has been studied for some while. All of these challenges have been tackled by various prior works, some of which I want to highlight. One is Liu et al., who showed 2v2 humanoid soccer in simulation, and more recently, Harnoja et al., who showed 1v1 real robot soccer. While both of these have impressive results and we build on these ideas, they both assume access to ground truth state information. And in this work, we want to extend to see if we can do this purely from vision, so onboard sensing and inference. Learning from vision introduces a number of challenges that we focus on. the strategies that you need are quite different because you need information-seeking behavior to self-localize, find, and track the ball as well as the opponent. You need memory because the environment is partially observable. And all of this increases complexity that we then need to trade off because we still want inference to be fast and running on board. So in this work, we present a general pipeline for 1v1 RGB vision-based soccer using purely onboard sensing and inference, which to the best of our knowledge is the first demonstration of its kind. So just to give a more visceral feel for what I mean by this complexity, let's take a look at the first-person view of a successful policy. This is what it looks like. It's a 40 by 30 render because it needs to run on board. You can see the agent can control its head camera, so it's quite noisy, a lot of movement. It's very hard to ascertain what's actually happening in this video. There's a lot of movement. We see a ball now, it's turning around, and then something seems to be happening. Let's take a step back and look at that again from third-person view. What was happening there was that the agent was first searching for the ball because it's outside its field of view. It fell down, causing the random camera movement. It's able to localize the opponent and the ball from very blurry frames, head towards the ball while avoiding the opponent, realize that it needs to score on the other side, so it goes around the ball and then shoots. So I hope that gives a sense of how complex the task is and that's why we were interested in solving it, right? So how do we do it? We train purely in simulation using a reward for scoring with some shaping terms, for example, for staying upright. The observations include proprioception and vision, and the action space is position control operating at 40 hertz. Now, because we want to train simulation from vision, there are a number of challenges that we need to address that are vision specific. For example, how do we render a real scene? How do we simulate the lab? We also need to think about learning efficiency because everything is slower now. Inference is slower, data generation is slower, and learning itself is going to be slower, which we need to tackle. And also we need to incorporate memory because the agent needs to remember its past, but also do it in a way that keeps inference costs low and can run on real hardware. So our goal, importantly, is to do this in a general way, making no task-specific or simplifying assumptions. So the way we tackle the first question is to use neural radiance fields, which I'm showing at the bottom here. So this is the scene from the real camera, and on the right is the simulated nerve scene. We also add various forms of visual domain randomization, including training with different nerves over time for scene variations. We overlay the dynamic objects like the ball and the opponent from the Mujoko simulation to create the full scene. We tackle learning efficiency by using replay across experiments, where we collect data from previous experiments and hyperparameter sweeps, which enables us to do efficient learning online and faster convergence. So here I'm showing a plot where learning from scratch is in blue, and when you use replay across experiments, we see the performance in cyan, so it really enables us to learn this challenging task. And finally, we incorporate memory using a ResNet encoder and an LSTM architecture, which allows fast inference and allows us to run on board. So here I'm showing the training pipeline introduced by Harnoja et al. And the changes in red are the vision-specific changes that I've discussed previously. They're quite minimal, just a nerve scene, replay across experiments, and a slight change to the policy architecture, which are general and should be applicable across beyond just this task. So with these simple changes, this is the behavior that we see, for example, in simulation. Notice the nerve rendering on the top right. This is what we see in simulation with the ball and the opponent overlaid. The agent learns to avoid the opponent, and then here it's actively searching for the ball when it's outside of view. And when the ball does come into view, it plots its trajectory, increases its speed, and shoots to score. So quite complex, long horizon behaviors that just emerge with no additional incentive, just from the scoring RL reward. We can then transfer this to the real world, and this is what it looks like. The egocentric agent view is shown in the bottom right here. I want to highlight a slightly different behavior in this video where the agent learns to use its body to block the path between the opponent and the ball. So here it uses its body, goes around the ball, and then tries to score. When it scores, it doesn't have the goal information in view. So it needs to clearly use its memory in order to remember where the goal was and then shoot and score, as we see here. We then carried out further analysis where we take the frozen fixed encoders of a trained policy and then train additional neural network heads on top of it to predict quantities of interest. So for example, in this here we're plotting the ground truth ball location as the red cross and a heat map showing the agent's prediction of it. As you can see, when the ball is in view, the agent really does quite well localize the ball. But importantly, Even when it kicks the ball, it can predict the movement over time. This just emerges naturally through training. We can carry a similar analysis on the real robot, as shown here, where on the left, we have the egocentric view given to the agent. In the center is the agent's global position, and on the right, the location of the ball. Again, we see that early on, it's a little more noisy, but as the ball comes into view, the predictions are quite accurate, and the agent can predict the movement of the ball after shooting it. We have a lot more analysis and interesting videos in the paper and on the project website, so I'd highly recommend you to check it out, that include quantitative results and comparison to state-based agents, more analysis of the object tracking that I showed before, and generalization tests to test whether the vision-based pipeline is generally robust to various quantities. For example, what happens when we print out an opponent, because this was trained from simulation, and it learns to stop, and also whether the kicking behavior generalizes to objects like balls of different colors and sizes. For example, kicking this basketball in this case, and also orange toy foxes. So the kicking behavior does generalize, thankfully. There's some interesting directions for future work that I've listed on the left here, including how we can scale this up to sort of more agents, improve perception using new sort of modifications to nerves, including Gaussian splatting. But we can discuss all of this as well tomorrow in our poster session at between 4 and 5:30. So please come by and say hi. Thank you.
Questions? Over there? On the lower half?
Maybe this one first.
Thank you very much for the talk. So how, the global localization happen through the same mechanism, vision-based, or the global localization is given to the robots?
Sorry, global localization?
Yeah, so where they are on the field, if they infer themselves, yeah.
Oh, sorry, so this was done after training. So we train the policy, there's just the regular reward. After we have a trained policy, we use the features that were learned and then train an additional head on top with the frozen features to see if we can predict these various quantities, right? So it's not done during training of the actual policy for scoring. It's just that it's a test that shows us that the features do track things like the location of the ball and the velocity, etc. Yeah.
And can I ask a second question?
I'm happy with that.
So how does your approach compare to a state of the art from the RoboCop community?
That's a good question. So the RoboCop community, actually, what we do is a much simplified version, yeah, because the RoboCop is actually a lot more complicated. They have fouls, throw-ins, etc. I think a fairer comparison is to the state-based agents that were presented by Hanoja et al. And we have a comparison in the paper that these agents are similarly agile, so they turn as fast, kick as hard, and generally move as well. Overall, the agility remains the same, I'd say.
Thank you very much.
Let's thank the speaker.
Thank you.
Okay, there was one last question. Okay, you want to ask it?
Hello? Yeah, thank you. How far away do you think we are from letting a team of humanoid robot to play against a team of human being decently?
Okay, that's a tricky one to answer. How far away is I don't like to give timeline estimates. I'm hoping that, with this work, people will build on it and that timeline is shortened, let's say that. Yeah. Thank you.
All right, thank you. The correct answer is always 10 years. It's always 10 years away. All right, so next up we have Wakoko learning whole body humanoid control with sequential contacts. And we have two speakers, Chang Zhang and Wenli Zhao.
Okay, thank you. So hello everyone, my name is Chong and this is Wenli Xiao from CMU, and we are here presenting our work for enabling humanoid to execute sequential contact tasks like these videos. And recently there are a lot of humanoid works, especially on how to map human motions to humanoid, but sometimes we don't have such human references for many different tasks. So especially for sequential contact problems, a typical solution is to use a model-based method, which has classical pipeline that first plans the contact and then plans the motion and then tracks the motion with whole body control. And typically, the robot needs to fulfill both contact constraints and task goals at the same time. And this pipeline has some limitations. For example, in contact planning, we need to plan each contact. And also, for motion planning, it can be very time consuming and it can need a simplified dynamic model. So it can affect real-time computation and also agility. And also, the control can be susceptible to model mismatch. So we wonder whether we can achieve something that only needs some key context states and can achieve real-time agility and also robustness. And we know that reinforcement learning is good for agility and also for robustness. But so we think IO can help here, but we also know that IO tuning is very tedious. And for sequential context, a typical practice is to design a finite state machine and then engineer policies for each state transition. So this takes a lot of efforts and cannot scale to different tasks. So here we want to make IO tuning easier for sequential contexts. So the question is, can we design a general IO framework for whole body control with sequential contexts with task agnostic designs to make tuning easier and without any motion prior for flexibility?
Okay, so we find that many tasks can be decomposed as a sequence of contact goals and task goals. So what does it mean? Let's take a look at this parkour jumping example. The robot is jumping over the stepping stones step by step. And if we only take a look at the second stone, we can see, wait, 1 second. Here on the second stone, we command the robot to have like right foot on the stone and left foot in the midair, while the upper body maintaining a hugging posture. So here, the contact goal is how the robot and the effectors should interact with the world and the objects. And the task goal is like other requirements, like irrelated to the contact. In this case, the upper body posture. So with such decomposition, this difficult parkour task can be decomposed to 4 stages. So each stage has its contact goal, like for example, the both foots should have contact with the stone or just left foot have contact. And the upper body task goal is to maintain a hugging posture. So with such decomposition, we can define a lot of tasks that's common in our daily lives, such as local manipulation. If you want to carry a box from one place to another, you just need to like define the contact sequence on the like 2 hands. And if you want a robot to dance for you or traverse a very narrow cliff, you just need to like define the contact sequence for all these end effectors. So with such decomposition, we propose our minimum reward design. Our reward function has 3 terms. The first is Wakoko reward, which is related to contact. And the second is regression reward, which is very common in the reinforcement learning community. It's just minimize the action rate or dot velocity. And the third term is task reward. So for the first 2 terms, they can be shared for all these different tasks. You just need to change the definition of contact, and you don't need to tune the parameter or rewrite the function every time. And for the task reward, it's usually very intuitive and straightforward, just 1 or 2 terms. For example, for the parkour, we just regularize the upper body joint angle. For the local manipulation task, we minimize the distance between the box and its target. And for the Wakoko reward, we want to motivate the robot to fulfill the contact sequence. We have 3 terms. The first is contact reward, the second is stage reward, and the third is curiosity reward. So we delete the technical detail here, but the design philosophy is to try to make the reward as dense as possible. So for example, for the curiosity, we propose a neural hash-based curiosity. So here we randomize, initial randomized neural network and use it to compress the high-dimensional state into low-dimensional binary hashing embedding, and maintain a count bucket to calculate reward. In practice, our curiosity function is very effective and crucial. Without it, the robot cannot learn these natural parkour jumping gates. So the next step is to leverage our vocoder decomposition and reward design to train a reinforcement learning policy. It's a cliche, just some sim-to-real transfer skills like domain randomization. So with our vocoder design, the policy can be very robust. Even my co-author Chong bullying the robots, it can still recover. For example, recover from kicking. And here the robot is trapped by this wire. It can keep moving this box. And here, even during the very agile jumping, the ground is sleepy, the robot can still jump. Yeah. So, On top of this, we don't want our robot to be isolated in the lab space. We want it to work in our daily lives. So here in this demo, there is a human holding a board that helps the robot to balance and passing a very narrow bridge. This showcases our robot has a capability to work with human. And finally, our framework is a general framework for all the robots that has contact requirement. So here we showcase to deploy this vocoder on a 2022 DOF dinosaur robot, dribbling the ball to draw the vocoder characters. And a fun fact is they are dribbling the ball using different end effectors. And that's all about the presentation, and thank you for listening, and welcome to our poster session tomorrow.
All right, questions for the speakers? Going down here.
Thanks for the cool talk and the very cool demos. So if I counted correctly, you have around 6 components in the reward function. Can you say something about how robust it is to the weighting of those?
Sorry, can you repeat the question? I'm a little bit lost.
You're asking about the relative weighting of those reward terms on your slide?
You mean the weights of the reward terms? Well, so each reward has its own weights, so they are quite different. For example, and we also have some reward scheduling. For example, for the curiosity reward, it is very large. It's 1,000 at the very beginning, but our scheduler will decrease the weights as the robot learns those skills. Yeah. So, and we also open sourced our code. If you are interested, feel free to check it. Yeah.
But generally, I want to say that the skills of the weights are similar to each other across different tasks. It's just not so much tuning compared to other IL works.
Other questions? So I guess one of the things that's an opportunity for RL is that you can, in many cases, abstract away all the messy details of contact interactions and just let the policy handle that implicitly. So it's sort of interesting that you put contact specification first and foremost in how you're describing the task. I'm wondering if you can think of tasks where you maybe wouldn't want to use this approach, either for locomotion or manipulation.
Yeah, because this method is specifically developed for certain tasks that require a specific contact sequence, but there are also many tasks like locomotion where the major goal is to balance the robot itself and not to achieve a specific contact pattern. So I believe this is not a cure for all solutions. It's just a solution for a certain range of tasks here.
Awesome. Thank you so much. All right, thank our speakers again, please.
All right, and the next presentation is by Hirsch Sangvi with OCAM, Online Continuous Controller Adaptation with Meta-Learned Models.
Let's see here. I think you're fine. Can we get the screen? Can we get the screen? Maybe try again.
Can we get a screen up there, please?
It's coming. Yeah.
Okay, okay.
Perfect.
Great.
Beautiful.
Okay.
All right. Hi, my name is Hirsch, and I'm here to present our work, OCAM, Online Continuous Controller Adaptation with Meta-Learned Models.
Sorry, the screen is out again.
Oh. I don't know what's going on.
Might be a connector. Let me try this one. So another one here. There we go.
There we go. All right.
Beautiful.
Sorry about that. So to motivate our work, tuning robotic controllers is a significant challenge. These controllers are highly sensitive to the values of their parameters and typically require time-consuming tuning, usually using heuristics that don't actually align with the downstream task of the robot, such as gain tuning a quadrotor using its step response. This is further exacerbated by factors such as the sim-to-real gap, which we've heard a lot about today, which means that controller tuning must often be done on the real system, as the simulated dynamics will not match the real dynamics of the robot. Furthermore, the optimal controller gains can change if the robot enters a new environment or its physical attributes change, such as picking up a payload, encountering new forces, or part degradation. Existing methods for solving this problem, such as adaptive control, Bayesian optimization, meta-learning, and combining online system identification with reinforcement learning, have shown great results, but usually require many assumptions about the controller or system, such as linearity or differentiability, or rely on prior or pre-trained models from simulation only, or require many trials or human interventions to adapt. Our method borrows ideas from each of these great approaches, but our goals in this work are to develop a framework for controller adaptation that learns a useful prior, adapts quickly in the presence of domain shift, without making strong assumptions about the system dynamics. The key ideas in our method are first, to learn a prior model to predict upcoming high-level closed-loop controller performance based on the control gains and the history of the system, such as sensors and actions. Second, to parameterize the model with a low-dimensional weight vector that is adapted using Bayesian estimation to data received from a robot with different unknown parameters, such as different masses, frictions, and more. And lastly, to use the adapted model as a cost or energy function to optimize the control gains during deployment. And the 3 steps of our method are run in a loop, as shown in the figure on the right. So first, how do we predict controller performance? We train a model that predicts future high-level performance measures as a function of control gains, task, such as the trajectory we want the robot to follow, and the recent sensor and action history of the robot. The performance measures are selected by the designer based on how they want the robot to behave. These can include terms such as the tracking error, the control effort, stability, the speed, and more. Importantly, the performance measures should be selected, quantities that can be computed using the information available on the robot, such as its sensors. The model's predictions consist of a weighted combination of learned basis functions, denoted on the slide by phi. We model these learned basis functions with a neural network, which remains fixed at test time. As we deploy gains and receive observations from the robot, we iteratively compute the weights using a Kalman filter with identity dynamics. Essentially, we're using the discrepancy between our observed performance on the robot and the predictions of the model to adapt these weights. The Kalman filter is an appropriate selection for this setting, as it naturally computes the variance of the weights, which will be useful for downstream decision making, it allows us to specify a prior on these weights, which is useful for allowing our model to make decent predictions without a lot of online data from the robot. It naturally handles time-varying systems, so systems whose parameters might be changing, and it's computationally lightweight. So how do we actually obtain these learned basis functions? We would like to learn basis functions and prior regression weights that are suited for adaptation, which means that they span the variations in performance that we observed by changing the system parameters. And the key insight that enables us to learn these basis functions is that the Kalman filter update is differentiable, which allows us to meta-train the model with the Kalman filter in the loop. So each training loop consists of the following steps. Given a batch of simulated rollouts from the system with some hidden parameters theta. So basically, we randomly sample a bunch of controller gains, roll them out, and observe the system performance offline, and our regression priors and our prior neural network weights. We pick a random subset of the batch of some random size, and we iteratively apply the Kalman filter to fit to the data points in that subset, obtaining the final regression weights, denoted on the slide by WM. We use the final weights to compute the loss of the model on the entire batch, essentially testing the ability of the model to adapt to data. And finally, using the differentiability of the Kalman filter, we backpropagate the loss to update the neural network weights and our regression prior parameters. We repeat this in a loop until the model is converged. In each iteration, we pick new random system parameters, essentially doing something like domain randomization. So once we've obtained this trained and adapted model, during deployment, we want to find gains that maximize the predicted performance in our upcoming trial. And because we've computed the uncertainty of our weights, we can actually propagate that and compute the uncertainty of our predicted performance, y hat, which enables us to use an uncertainty-aware reward function during optimization, such as the upper or lower confidence bound shown here. This essentially lets the designer select how risky they would like the optimizer to be, whether they want to weight towards exploration or exploitation of the information. To actually solve this optimization problem, we use a simple particle-based random search as the optimizer, essentially taking many randomly sampled candidate gains, collating them into a single batch, and evaluating them with a single forward pass through the model, which is extremely efficient on GPU and effective for many common controller gain spaces, which are relatively low dimensional. So the method we've presented so far makes very few assumptions about the system dynamics or the form of the system or the controller, and therefore it's readily applicable to a wide variety of robot and controller morphologies. In this work, we evaluate Occam to tune the controllers on 3 diverse systems. First, a simulated race car with a nonlinear PD controller and unknown mass, tire friction, and engine power. A simulated quadrotor with a geometric controller and unknown mass, inertia tensor, and thrust coefficient. And a simulated quadruped with a behavior-conditioned RL policy with unknown mass, friction, and motor strength. We train models for each of these systems by sampling system parameters from some training subset and generating the data. And then for evaluation, we sample system parameters exclusively from outside of the training data set, essentially testing the ability of our method to generalize outside of the training distribution. We find that across many different out-of-distribution system parameters and across all 3 simulated systems, on average, Occam outperforms meta-learning and Bayesian optimization baselines at fast online controller tuning in out-of-distribution environments. To show some qualitative results, our method on the left automatically optimizes the controller gains to compensate for out-of-distribution mass and decreased traction, allowing the car to stay on track, while the nominal gains do not allow it to do so. Our method also makes interpretable optimizations to the controller gains. When more traction is available, in the example on the right, Occam tunes the gains naturally to drive more aggressively, while remaining conservative where necessary. In the quadruped case, our method quickly optimizes the behavior parameters such as body height, stepping frequency, and stance width to compensate for lower friction and walk more stably. Our method also crosses the sim-to-real gap. Occam, trained only on simulated data, quickly finds control gains that result in lower tracking error on a real crazy fly compared to expert tune gains and an L1 adaptive controller, even under dynamic mass perturbations, which are shown in the video on the right. It's important to note that our method also runs in real time on a laptop without a GPU, meaning it's quite computationally lightweight. So to conclude, we've shown that predicting high-level performance measures and adapting the model in a low-dimensional space enables fast, generalizable, and online controller tuning. Future work includes extensions to more real systems, further analyzing Occam's performance from a theoretical standpoint, and exploring more sophisticated optimizers and exploration strategies. Please visit our poster tomorrow during poster session 3, and check out our project page for more results and experiments. Thank you.
Questions? Over there.
One thing is your method really learning how to deal with unknown mass inertia, or like in the car example, going on a straight line and the future is a curve taking a turn, right? Are you saying that it's able to figure out how to take the turn, the right gains for the turn based on how it is driving on a straight line?
So the notion of actually driving a straight line versus taking a curve is captured by the task variable that we feed our model. So there's this, oh, I guess it disappeared. So yeah, we feed some notion of the upcoming trajectory to our model. So it's allowed to select its gains based on the upcoming task.
Next question, up there.
Yeah, thanks for the nice talk. One more question. Yep.
Yeah.
So it feels like you've put together a fairly advanced variation on what's basically a gain scheduled nonlinear controller. And that ought to be tractable for a formal stability proof. Have you considered doing a proof? Do you have such a proof, or is that on work in progress?
That is a work in progress, but I agree. All of the components of the method kind of lend themselves to being able to do this proof. But that's something we're working on, and don't really have anything to say about that quite yet. We can make some statements about the optimality of the Kalman filter as an estimator when certain conditions are applied. But whether or not the learned basis functions satisfy those assumptions and whatnot is still remains to be seen.
Thanks.
One last very fast question.
Push on it? Or? Yeah. Yeah, thank you for the talk. My question is regarding the model that you use. So this is like very similar to like Bayesian last layer models that are quite common right now. And I think there exists an approach that is also some few years ago where they also do like backpropagation through like Kalman filtering. Can you maybe touch a little bit on differences there, I guess?
Yeah. My understanding, if I'm thinking of the paper that you're talking about, is they don't explicitly consider a Kalman filter parameter, a Kalman filter interpretation. They more look at it as like a online linear regression, and so they don't have some of the extra parameters that the Kalman filter introduces, notably like the Q and the R matrices, which are important. For example, if your system is time varying, you need to know like how quickly should I change my weights. And there's a couple of other differences, such as I think those were learning like a low-level dynamics model, and we're explicitly learning like a high-level model explicitly for controller tuning.
Okay, let's thank the speaker.
Should I just restart it? Maybe we can ask the person.
Would the speakers for paper number 6 please come down? We might swap the order of these two talks, just so we have more time to sort out IT issues.
Okay, let's do that. Okay. Looks like they're here.
Okay,
so we'll have you come up, and we'll restart your computer.
Yes.
So this is Okami.
Yes, it's Jinhan and Yifeng.
All right.
Okay. Do you have any audio?
No.
No, just the screen. Okay.
Cool.
Should be previews here, and that'll be what you see on the screen.
Let me.
Yeah, sorry for that. We had some IT issues. We're going to sort out with the previous presentation. So we will swap the presentations, number 5 and 6. Okay. So these are Jinhan Li and Yifeng Zhu. presenting Okami, teaching humanoid robots manipulation skills through single video imitation.
Hi everyone, I'm Yifeng Zhu.
And I'm Jinhan.
Okay, yeah, today it's our great pleasure to present our new work on humanoid from single video imitation. So most of us, if not all, would definitely want generalist robots in our home doing a lot of household chores, right? But then, humanoid robots nowadays, you've seen all these trending booms with their human-like embodiments can naturally fit into the environments because it's actually designed for humans. Also, because of their human-like embodiments, it's more possible to perform a wide range of dexterous manipulation tasks in our everyday environments. So now we've seen great advancements in the hardware designs, and also many companies have shown great demos. You can see on the first floor. But however, despite their great potential, humanoids struggle to autonomously interact with objects through their open world perception. So data-driven methods like learning from demonstrations render themselves a viable path towards teaching more natural movements for the humanoid robots. But where does all this data come from? In prior work, researchers have mainly investigated two categories of work. First one is using kinesthetic teaching. While it's very intuitive for the researchers, it's actually very hard to control high degrees of freedom, and also very hard to teach natural movements when it involves involves more arms. There's another path, which is teleoperations. However, usually the teleoperation devices cost more money, and even if people have reduced the cost of them, it still requires excessive efforts to always operate the robots. So what's the more possible alternative? So researchers have looked into the learning from visual demonstrations, where the way of providing demonstrations is more intuitive, and anyone can provide them through video recording. However, most of the results require paired robot data, which still imposes a lot of efforts on the demonstrator. And also, it's hard to scale to humanoid robots, and they're only shown on tabletop manipulations. So how should we teach robots new manipulation skills in the easiest and most intuitive way? So we seek inspiration from how humans learn from their very beginning of childhood, as the underlying learning mechanisms reveals the most intuitive way of learning that humans will feel comfortable with. Let's check out this video from a cognitive science study decades ago, where the adults were teaching a baby new manipulation skills. Now notice that this young baby, who hasn't developed the ability of language understanding by then, look at how the adults perform the task, and can almost correctly imitate the task in the same way. And note that it comes so natural to her that this demonstration only needs to happen once, and the girl can immediately imitate. And she can imitate a lot of tasks, not only just a single hand manipulation, but also some object interactions that is definitely not natural to her. So motivated by this study, we envision a future where human and humanoids live together, and anyone can teach their humanoids a new task face-to-face using just a single video recording. So in such a setting, it is almost effortless to teach robots new skills, since no meta training or data pre-collection is needed, and also it does not require expertise because no control devices are involved in this whole process. However, it brings great challenge in this setting because, first, the videos are actionless, meaning that there's no ground truth actions for the policies to regress to, so you cannot use the common imitation learning pipeline. Also, it only requires single demonstrations, so that common imitation learning paradigm does not work here. So how do we tackle these challenges? We go back to the baby's example, and we have two key observations. The first observation is that the baby actually look at how the adult's hands move, so that she can understand how the arms and hands are moved during this manipulation. And the second one is object-centric, meaning that she was interpreting how the objects are being manipulated in this whole process.
Motivated by these two observations, we introduced Okami, which stands for Object-Aware Kinematic Retargeting for Humanoid Manipulation Imitation. The input to Okami is a single human video observed by the robot. Then, Okami would enable the robot to roll out in different spatial and visual conditions. Okami has two stages. In the first stage, we generate a reference manipulation plan from the video, which is a spatial-temporal abstraction of the video that tells the humanoid robot which objects to manipulate and how human would manipulate them. In the second stage, we synthesize humanoid motions through object-aware retargeting, where we map the human motions onto the humanoid robot while adapting to the object locations at test time. In the end, with the raw data generated by Okami policies, we show that we can use such data to train closed-loop visual motor policies without any teleoperation data. So how exactly does Okami work? We first use state-of-the-art VLM GPT-4V that comes with powerful common-sense reasoning ability to get the names of the task-relevant objects from the video. Then we localize and track these objects across the video using foundation segmentation model and object tracking models. Next, we identify the sub-goals based on object motions estimated by track endpoint models, detecting large changes in velocities using change point detection. We also estimate the human motion using a human reconstruction model, getting both the human hand and body poses at each time step represented by a simple H trajectory. Then we generate a reference plan. Each step of the plan includes a simple H trajectory corresponding to the segment and to the associated object information. There is a target object, which is the object in motion due to manipulation, and a reference object, which serves as the spatial reference for the target object. And in the second stage, we introduce a novel process called object-aware retargeting. To execute each step, we first retrieve the target and reference objects from and a simple H trajectory from the reference plan. Then we localize the object locations at test time using grounded SAM and estimate the transformation between point clouds to compute the goalpost of the target object. And we also retarget the simple H trajectory onto the humanoid robot using a factorized process which separates the retargeting of arm and hands. For the arm, we warp the human trajectory according to the current pose and the computed goalpost of the target object. Here, warping bends the trajectory to ensure that the robot arm can reach the objects in their new positions while maintaining the overall curvature of the trajectory. We use inverse kinematics to compute the joint configurations. For the hands, we use a package called DEX retargeting to compute the finger joints. Then we send the command to real robot for execution.
So here's an overview of how we deploy the Okami. So here's our lab video showing the demonstration of a bimanual bagging task to the humanoid. And Okami reconstruct the humans from the video and also track the objects, as we mentioned in the method section, so that the robot policy can generate a reference plan for the robot to imitate. So the robot can follow this plan and be deployed in diverse environments where we just use only single video demonstration. You just saw that Ming gave to the humanoid robot. What's nice thing about this is that now we can collect data without any teleoperation and then train the behavior cloning policies so that robots can reactively respond to the stream of RGBD observations, and the robots can manipulate text by manual manipulation. And also, we use the humanoid robot GR1 with the Intel RealSense camera and control at 40 Hz joint commands, which interpolate to 400 Hz in the low-level action.
We evaluated over 6 diverse tasks that covers manipulation behaviors such as pick and place, pouring, manipulation of deformable objects, articulated objects, and bimanual dexterous long horizon manipulations task. And we show that Okami successfully imitates these diverse tasks and that Okami can maintain good performance when imitating videos from different users. Here, the users are from diverse demographics and has different manipulation speeds and preferences.
Sorry. So now you just saw the robots can train the behavior cloning policies using the Okami rollouts, and then we show that as the policy rollout increase, the robot can increase the performance as we show. So in summary, we introduced Okami, which allows the humanoid robot to imitate from single video, and which shows strong visual and spatial generalizations. And also, Okami serves as a teleoperation-free data collection pipeline for training closed-loop visual motor policies. And with that, we still have a lot of limitations in Okami. And the major thing is that it limits to upper body retargeting and also requires depth sensor in the video recording. So the future work is to include lower body motion for local manipulation behavior imitation, and also use RGB-only videos. And with that, thanks for listening, and our poster session is also at tomorrow afternoon. And please come and stop by. Thank you.
Thank you. Questions?
We might have one quick question on that one, huh?
Did I see a question somewhere? There. Here in the middle, please.
Hi. When you perform the point cloud registration, do you assume to know the initial transformation between the 2 point clouds, or you're doing some sort of semantic correspondence matching?
So in this work, we mainly based on the point cloud, and can do like global registration. So it's based on the geometry heuristics. But yeah, that's a very good question. So like in the future, we can definitely use more like a large visual language model to do more semantic correspondence.
Any more questions while we set up this? Maybe another question from me. So you showed how you can use to mimic a single video demonstration.
Right.
So what is can you scale this also to just like YouTube data, YouTube videos?
Yes, so that's the whole point of doing this project. So we use RGBD video as input to understand what it takes to learn from a single video. And it paves the way for us to understand how we should learn from the RGB video, which is basically how we unblock the YouTube video data source.
Okay. Thank you. Thanks, speaker again.
All right, our last talk of the session is going to be Vocal Sandbox, Continual Learning and Adaptation for Situated Human-Robot Collaboration. Our speaker is Jennifer Grannon.
Hi everyone, I'm Jen. Thank you all for your attention and staying over. I realize I'm between all of us and dinner. So today I'm going to be talking about building an adaptable robot for situated human-robot collaborations, and this is joint work with Sid Karamchetty, Severe Mirchandani, Percy Liang, and Dorsis Sadig. So I want to start by zooming out. And we see that physical human-robot collaboration is a rich and exciting setting and these collaborations can take a variety of different forms. So for example, here we see the robot and the human are working together to stack a Lego block tower by alternating putting pieces on the tower. Now, while these works demonstrate really impressive adaptation and communication capabilities, they're relatively limited to toy settings with unrealistic objects, clutter-free workspaces, and prohibitively slow execution times. Moving towards more complex settings, we see that much of the work on reacting to human feedback in real time is limited to either high-level changes, for example, from language feedback shown here on the left, or for low-level skill learning. So in the case on the right, this is learning a reward function from kinesthetic feedback. These are great ideas for how to improve in situated settings, but what if we want to be able to learn and adapt at multiple levels of abstraction? And what if we wanted to be able to do that continually over the course of an extended interaction? We propose Vocal Sandbox, a framework for situated collaboration that enables teaching at multiple levels of abstraction, low-level skills and high-level behaviors. So for example, let's say Sid here wants to deploy a robot for stop-motion filming, where Sid is directing the film while the robot acts as the camera dolly. Sid might want to teach the robot new low-level camera motions to get the shots that he wants for his movie. To teach a new low-level skill, the robot first identifies that it doesn't know how to ground what Sid wants it to do to actions, and then prompts him to teach it.
I don't know how to fly up. Teach me?
In this case, Sid provides a kinesthetic demonstration to teach the fly-up shot that is used to fit the weights of a dynamic motion primitive, or DMP.
Okay, nice. Right.
Unlike prior works that assume a static set of low-level skills, A key contribution of Vocal Sandbox is the ability to dynamically grow the set over a course of an interaction. Sid might also want to teach new high-level camera behaviors for longer establishing shots. And to teach at a higher level, he gives step-by-step language instructions of how to compose the new behavior.
All right, can we get a shot of Iron Man taking off and flying up the tower?
I don't know how to take off. Teach me?
Okay, zoom in on Iron Man. Yes. Okay, now fly up the tower. Beautiful.
Vocal Sandbox utilizes interpretable and lightweight learning algorithms to learn at multiple levels of abstraction in real time. So for low-level skills, this means fitting the weights of a dynamic motion primitive from a user's kinesthetic demonstration. For high-level behaviors, this means adding newly taught behaviors to an API to be used with a code-based language model planner to generate robot plans on the fly. To evaluate the various components of Vocal Sandbox, we forego the Lego stop motion setting momentarily to run a systematic user study with non-expert users on a shorter task of assembling 4 gift bags with a candy, a toy, a tub of Play-Doh, and a handwritten card. So users choose to handwrite the card while delegating the task of assembling the gift bag to the robot. For earlier bags, users spend more time teaching complex, high-level behaviors. For example, here the user is teaching pack the toy car as pick up the toy car, go to the gift bag, and release the toy car. Users also teach relevant low-level skills for the task, in this case, visual groundings of the gift bag items to disambiguate between the large number of objects on the table. For later bags, users use their previously taught low-level skills and high-level behaviors to streamline the interaction towards their shared goal. We find that Vocal Sandbox systems require 22.1% less supervision, yielding lower bag assembly times. And zooming in on a specific user, we also visualize how they choose to spend their time throughout an interaction, categorized as either instructing the robot in orange, confirming the plan in gray, or parallelizing with the robot in blue. And as expected, we see more instruction time spent on earlier bags and then more parallelized time in later bags. We find that Vocal Sandbox systems are also capable of adapting both high-level behaviors and low-level skills over an interaction with 19.7% more complex autonomous performance and 67.1% fewer skill failures compared to baselines. Finally, users also prefer Vocal Sandbox systems over all baselines due to its ease of use, helpfulness, and overall performance. Now, it's great that Vocal Sandbox is usable across a wide variety of users, but at only 10 minutes, this task is still relatively short. So we wanted to know what could we do if we really tried to push the interaction to the length of hours. Now we return to our stop motion setting, which requires human creativity and enormous amounts of effort to arrange the Legos and also precisely maneuver a camera, often simultaneously. And in fact, people often need assistance to manage all these responsibilities, and this seems like a role uniquely suited for a robot collaborator. Thus, we consider an extended interaction setting to shoot a Lego stop motion animation where the robot acts as a precise camera dolly, freeing up the user to do the creative aspects of the task, like writing a script, arranging the Legos, and then directing the movie. The length of the interaction made running a full user study difficult, so we consider only a single experienced system user, me. Here we show the full 2-hour interaction on the left, as well as the final stop motion animation film on the right. The final film is 52 seconds long with 232 frames, of which 43% are shot completely autonomously from 40 novel user commands. In conclusion, we present Vocal Sandbox, a framework for situated human-robot collaboration that is capable of adapting at multiple levels of abstraction. In the future, we hope to push this framework towards more realistic settings, moving from the interaction scale of hours to days, and with more seamless interactions like Tony Stark and Jarvis here. Concretely, we're actually in talks with local shops like bakeries and cafes to use our system to help with time-intensive tasks like portioning dough, cutting vegetables, and mixing batter, all adapted to each shop's specific needs and setup through interactions with the employees. So stay tuned if you're looking for a robot sous chef. And thank you so much. Happy to take questions, and I hope to see you all at our poster tomorrow afternoon.
All right, questions? One over there.
Can you hear me? Okay. I really like the Lego filling part, but I think the human is still doing the position of the characters. What do you think will be the possible way to extend your current framework to enable the robot autonomously, like doing this like fine-grained manipulation to like in the animation task?
Yeah, I think part of it, you're asking about like the position of the characters, having like a more grounded planner, like using a VLM instead of an LLM or something like that. As far as dexterity, I think being able to have really interpretable and easy to use like interfaces for end users to teach the robot more dexterous capabilities. So there's kinesthetic demonstrations, but you also might want to teach in a more grounded way that's like grounded to point clouds or something like that. So I think a lot of it comes down to like the representation and the interface.
Okay, thank you for your answer.
Other question? Okay, I can ask one. What was the most surprising observation from your inexperienced user study?
I think a lot of things that I take for granted, users don't know. So for example, being able to teach in a modular way, like people choose to define actions very differently. So where I would teach something like pack or put in bag or something like that, people will teach like pack toy car, pack candy, pack, you know, and so the intuition of like functions and arguments isn't always clear, especially to someone who hasn't programmed before.
Now, is it easy for someone to go back after they realize that and sort of change the functions and abstractions that are being used?
In this setting, we didn't consider that, but I think it's totally something that is, you know, can be added and would make it more usable.
Awesome, thank you. All right, I think we could wrap it up here. Let's thank our speaker one more time.
So with this, we also conclude the day one. So there's a banquet at 7 p.m. The details are on the CoRL website. If you take the metro at 6:30, you should be able to reach by 7. So we look forward to having you at the banquet, and we start tomorrow at 9 a.m.